Now we return back to Euclidean geometry, and in specific circle geometry theorems. So we'll start off with some definitions. Important that we know. What is a radius? A radius is any interval joining the centre to the circumference. A diameter, on the other hand, it's also an interval, but it also goes through the centre, but it joins any 2 points on the circumference going through the centre. Diameter. Chord, that's also an interval, but this one joins 2 points on the circumference, but not necessarily going through the centre this time. So of course that means the diameter is a special type of a chord. A secant, it's not an interval, it's a line. So therefore it cuts through the circle because it keeps going in either direction there. A tangent is a special type of secant. It's one that doesn't cut it in two places, but of course touch it in just one place. Arc, well, that's just a piece of the circumference. So I've just labelled in an arc there, but actually I've created two arcs. The small arc's known as the minor arc, the larger arc is the major arc, and we usually assume the minor unless they tell us otherwise. Okay, sector. Now we're talking about shapes. This shape has as its boundary two radii and an arc. And once again, I've actually got two sectors there, the minor sector and the major sector. So the minor sector is what we call the piece of the pie. The major sector is if you're incredibly greedy. A quadrant is a sector, but where that angle at the centre would be 90 degrees. So it's quarter of the circle, hence the prefix quad. Segment, also a plane figure, but this time its boundaries as a chord and an arc. And once again, there's two segments there, major segment and the minor segment. Again, our semicircle is a segment, so it's also a sector. It's both. Concyclic points. They're points that lie on the same circle. So they're concyclic. So A, B, C and D are concyclic points. You don't have to have four, of course, you could have any number of points. The reason I've chosen four is to go to our next definition. A cyclic quadrilateral, which is a quadrilateral whose vertices are concyclic. So all four vertices lie on a circle. We call that a cyclic quadrilateral. This is what we call subtending an angle. To subtend an angle, you get 2 points and you join it up to a third point. So you subtend from 2 points. So we say alpha there would be subtended at the centre, but by the arc AB. So it's come from the 2 points AB, joined up to a third point in the centre. Now I've said the arc AB, it could also be the chord AB. Problem is when you say the chord AB, you don't know which direction you're going. So that's why we tend to say arc AB. And again, I assume the minor arc unless specified. That one there would be the angle subtended at the circumference, also coming from those 2 points AB. And that might remind you of a theorem that we will look at later, but you may remember that one. They're concentric circles. Concentric circles have the same centre. Okay, these are what we call circles that touch internally. So one circle is inside the other, but they only touch at one point. Thus they share a common tangent. But you can also have two circles that touch externally. They also share a common tangent. So that's just some basic definitions, words we use in circle geometry. The theorems. We're now going to look at the chord or the arc theorems. The reason I've put both words there, again, if you're talking about the end points, you could be talking about the arc, you could be talking about the chord. So it's really the same theorem. Equal chords will always cut off equal arcs. Okay, so if you've got chord of, I don't know, 3 centimetres on one part of the circle, a chord of 3 centimetres on another part of the circle, then the arcs that join those two endpoints must be equal in length. All right. Ooh. Here it is in its long description. A perpendicular drawn to a chord from the centre of a circle bisects the chord, and that perpendicular bisector of the chord passes through the centre. What a mouthful. What are we talking about? Much better, the abbreviation. The perpendicular from the centre will always bisect the chord. So perpendicular from the centre bisects the chord. So in my diagram there, if I know that that is a perpendicular, then I can conclude that AX is equal to BX. Perpendicular from centre bisects the chord, but let's go and prove it. So all we know is that AB is perpendicular to OX. I want to prove that AX is equal to BX. Most of these proofs are done with congruent triangles. So let's create some triangles. I'm going to join up OA and OB, so a couple of radii I've drawn in. And now I can get congruence. Well, they've told me those angles are 90 degrees. Well, they told me they were perpendicular. AO and BO are both radii, and OX is common. So we have right angle, hypotenuse, side. Well, in that case, they're congruent, and that means AX must equal BX, matching sides in congruent triangles. Ooh. Okay, the converse of that. So the converse just means reading the theorem the other way around. In the first one, I knew they were perpendicular, therefore they were equal. If we go back the other way, this one is simply saying, well, if I know they're equal, therefore they're perpendicular. So let's draw a picture. So this time what I know is AX equals BX, but from that I should be able to conclude that OX is perpendicular to AB. Write it slightly different because now the information we know that they're equal. So what I'm saying here is, hey, the line that joins the centre to the midpoint must be perpendicular to the chord. So let's prove this one. Once again, we'll do it via congruent triangles. So I'll draw in a couple of radii, but this time I've got AX equals BX, so I have a side. I've got 2 radii, another side, and I have the common side. So side, side, side is how I'll prove congruence. Well, that now means that AXO must equal BXO, angles in congruent triangles. Well, there we also know they add together to give 180 because that's a straight angle. Well, hang on, if they're equal and they add together to give 180, then I must be able to conclude that AXO is 90 degrees. Thus, they're perpendicular. Equal chords of a circle are the same distance from the centre and subtend equal angles at the centre. All right, so what we're saying is OX must be equal to OY. The equal chords are equal distance from the centre. I also know that angle AOB would be the same as COD. The angles at the centre would be the same. Well, let's go and prove, first of all, we know AB is equal to CD, they're equal chords. And I also know OX is perpendicular to OY, because whenever you're finding the distance from a point to a line, it's always the perpendicular distance you're interested in. Okay, so I want to prove that the same length. Once again, let's draw in some radii to create a couple of congruent triangles. I've got OA and OC. Well, AB equals CD. They gave me that. They're equal chords. Well, AX must be half of AB. I should have written perpendicular from centre bisects the chord, but perpendicular from centre bisects the chord. And same reason for CY is half CD, but if AB is equal to CD, therefore it's fair enough to say AX is equal to CY. They're both half of the equal chords. Okay, AXO is equal to CYO is equal to 90 degrees. And we have OA equals OC, they're the radii. So we have right angle, hypotenuse, side. We know they're congruent. Therefore, OX must equal OY, matching sides in congruent triangles. Now let's prove those angles at the centre are the same. So again, all we know is they're equal chords. This one's a lot easier to prove because they're equal chords. So AO equals BO equals CO equals DO. I mean, they're all radii. Beautiful thing about geometry, it's not an equation we're solving. So we can write more than one equals on a line, which is saying, hey, we're listing all these things are equal. We got side, side, side. Thus, AOB is the same as COD, corresponding or matching angles in congruent triangles. Okay. All right, there's the first of our angle theorems, and of course you don't have to prove them each time. I mean, that's the whole point of having the theorems, so that we save ourselves a lot of time. We can just use that information to then go and prove whatever it is they're asking us to prove.